All right, what's going on, everybody? Today we're doing another LeetCode problem. This one is called Koko eating bananas. It's a medium. Let's get into it. So Koko loves to eat bananas. Koko is a gorilla or a primate of some kind, presumably. I mean, this is a lot of bananas. So, anyways, they're in piles of bananas. The ith pile has piles I bananas, and the guards have gone and will come back in H hours. Basically, what that means is we have this array here called piles, and each element in that array is going to represent a pile, and then the value is going to be of that element is how many bananas are in that pile. And then we also have this integer h here, which is just like how many hours. There's some guards, they're going to be gone for h hours. That's how long Koko has to eat the bananas, and she's got to eat all of them. So she can decide her bananas per hour eating speed of k. Each hour she chooses some pile of bananas and eats k bananas from that pile. If the pile has less than k bananas, she eats all of them instead and will not eat any more bananas during this hour. So what that last sentence means, basically, if the banana eating rate is like 11 and she was at this pile 3, she could only eat 3 bananas and she'd have to wait for the hour. Like, she can't eat 3 and then in the same hour go to this pile. Like, basically you can only hit one pile every hour. So like if the banana eating rate was 11 or 12 or 13 or whatever for this example, the maximum hours here would be that it would take would be 4. Or the minimum hours you could eat all of those bananas would be 4, because you have to spend at least an hour on each pile. So anyways, yeah, Koko likes to eat slowly but still wants to finish eating all the bananas before the guards return. So basically, yeah, she's gonna be eating them all before the guards get back in H hours. And they want us to return the minimum integer k. And remember, k is like the velocity. It's like the bananas per hour rate. So they want us to return the minimum speed, the minimum bananas per hour, k, such that she can eat all of the bananas within that upper bound of H hours. So there's kind of a lot of moving parts for the problem statement. Honestly, it's not the most like straightforward, but we'll roll with it. So yeah, basically the optimal solution here, and even the like quote unquote brute force solution for this problem is like really hard to derive. So I'm just gonna get into the optimal one. Like, I think the difference, like if you could derive the brute force solution, I think it's so difficult to derive that there's like a marginal difference in difficulty between the brute force and the optimal. Like if you can derive the brute force solution, you could probably figure out the binary search optimization to make it optimal. But anyways, we're just going to go straight into the optimal one. So the optimal solution for this problem is going to entail using a binary search for the minimum speed or the minimum rate k. And then so like probably, so if you're thinking about, okay, like how are we going to use binary search to solve this problem? Like what, so right, we're going to be using binary search to search across different values for k, but how do we even know like what range to search through, right? Because all we're given is like a bunch of piles of bananas. Basically the answer there is, well, we can look at the constraints of the problem to figure out the range for possible values of k. So the minimum rate is going to be 1, because there's going to be at least one pile, and that one pile is at least going to have one banana. So she's got to at least be eating one banana per hour. So basically we can say our left pointer is going to be just 1. That's going to be the minimum rate for k. Now, what's the maximum rate for k? Well, obviously, I think we were kind of looking at this before, right? So it's like if the rate for k was like 11 or 12 or 13 or whatever, we know that we can only hit one pile per hour. So like for this problem, even if your rate was like a million, it's going to take you 4 hours to eat all of these bananas because you can only hit one pile per hour. So with that in mind, we know that our maximum rate for K is just going to be whatever the maximum pile is. So our right pointer is going to be just the max of those piles, and to do that, I'll just do that manually here. So we'll just iterate over the pile for every pile in piles. We basically want to set the right pointer to be the maximum value of between whatever the previous maximum was and then the current pile we're looking at in the array. So that'll give us the maximum rate K there for the right pointer. And now at this point, there's only a few more variables we need, and we can get into the search algorithm. So we have the left pointer and the right pointer. We're also going to need a variable for the result. So we can just call this res, and at first we can just make it equal to that top speed, because we know we'll definitely be finished in under the amount of hours they give us based on the constraints as well. Notice how the hours is going to be greater than or equals to the number of piles there are, so we'll always be able to finish the bananas. With that being said, we can set the result to the max rate there, so we can just set that to right at first since we already calculated that max. We also need a midpoint, but I'm not going to calculate that yet. We're going to update that with each iteration, but I'll declare it there so we don't have to reallocate every single time the loop iterates. So we're going to do while, and let me move this over and give us a little more room here. So we're going to do while our right pointer is not overlapping with our left pointer, so pretty typical for binary search. And then the first thing we're going to do is calculate our midpoint between those left and right rates. So the rate that is exactly between those will just be the average of them. So to find the average, we can just add them, divide them by 2. And then basically we want to know for this particular rate K we're considering, which is the current rate K we're considering here is the midpoint. It's like, how many hours total is that going to take to eat all of the bananas with this rate, and is it going to be within the bound H that they gave us? So the way we can calculate the time it's going to take is we're actually going to need a double, because we need precision. For the time here, it can get really big. So in C++, we need to use a double there. We'll call it time. We'll set it equal to 0. And then we're going to loop through these piles once again. I'm just going to copy and paste this. We'll have different stuff inside of the for loop, but the for loop itself, the range there will be exactly the same. So we're just going to loop over those piles, and basically we're going to keep adding the hours that it takes to eat all the bananas in a pile. So just to see how we're going to do that, it's like if our rate is like, I don't know, 4 here, if our rate K is 4, basically it's going to take us 1 hour to eat all the bananas in this pile. And we know that because we're going to just take the ceiling of the current pile we're at, and we need to cast that to a double, but the ceiling of the current pile we're at divided by that rate that we're eating the bananas at, which is the midpoint. So for a rate 4, that would obviously take 1 hour. For this pile, it would take 2 hours, because we could only eat those 4 bananas in 1 hour, and then we'd have to spend a whole nother hour eating the last 2. And that would work because our pile is going to be 6 divided by our rate, which would be 4. So that would be, 1.5. And then we take the ceiling of that, which would be 2. So, and then 2 hours is the correct number of hours there. So we can use that for every scenario here. This is the formula. And then, so now that we have the time, we basically want to use that time depending on whether or not it fits this upper bound here. We can set it as a result, or just keep searching the other direction. So basically, if our time is that it's going to take to eat all the bananas with the current rate we're looking at, if that time is greater than, or sorry, less than or equal to the rate h, or not the rate h, but the upper bound h they gave us. So if it's below that upper bound, we know this could be potentially the answer. So first we're going to set the answer to, remember we're looking for a minimum time here, so it's going to be the minimum of whatever the best time we found was, and the minimum of the best time we found, and the, so res, and then the current rate, so midpoint. Because remember, we're looking for the lowest possible rate. So, and then after that, we're just going to update our, let's see. So we need to search for times that are potentially even shorter than the one we just found. So to do that, we're going to shift the right pointer downwards to be equal to the midpoint -1 to look at the lower half of those rates. And then if we don't have to do anything or any queries now, because we know that the time at this point would be greater than h. If that's the case, we can search for times that are greater than the time that we just found, because we know we're allowed to, right? We haven't reached that upper bound. So the left pointer will be equal to the midpoint +1 in that case. And then let's see. So after this, we can just return the result. And that's pretty much it for the problem. So this problem is going to have a time complexity. Let me zoom out a little more because it seems like I'm scrolling a lot here. So the time complexity for this problem is going to be, let's see. So we're basically going to be looping through, so let's see, let me write a note here. So our time complexity will be big O of basically the max pile. So I'll just call this max piles. So, because that's how many times we're going to be doing this binary search. So actually, really, it's going to be like log of max piles because of the binary search. It's a lot of parentheses. And then it's going to be times something, right? Because within this binary search, we're doing a linear search for to calculate, how much time it will actually take to eat all the bananas for this whatever speed we're looking at for this. So it'll be max piles times, I'll just say n, where n is like the size of piles. Yeah, so that's pretty much it, and there's no extra space complexity. So as in space is constant. So space is going to be, I'll just make sure I specify that. So space will be constant. So yeah, let's just go ahead and submit this to see how we did. So it beats 97% with runtime, 63% with memory. So yeah, there's a few other optimizations you can make. Like I know you can actually get it even closer. Like you can decrease the size of this binary search if you shift the left point. Like there's a way you can make the left even higher and exclude unnecessary searching. But the thing is, I think for that optimization, like this problem is, I mean, that part of the problem is a binary search, right? That goes by lightning fast. I don't think adjusting the bounds is going to do any good for you, to be honest, or do much good at all. And then I heard some people talking about like you don't need this min here, so maybe that's true, but I'm not gonna mess with my algorithm too much because I know that it works and the time complexity is decent. So anyways, yeah, I hope this video helped you understand this problem more. If it did, be sure to like, subscribe, all that stuff, and I'll see you guys in the next. Peace.